Hi, in this video, we are going to continue with our section on combinatorics. And here we are going to look at two different counting methods. One is the correspondence method and the other is the method of recursion. So to introduce the techniques here, what I will first define are the basic types of functions that we might want to look at. Okay. So let's say X and Y are two sets, So suppose for each X belongs to capital X, there is a unique element Y that belongs to the capital Y set. Then this means that we have established a function or a mapping from set X to set Y. Mapping from set capital X to set capital Y, right? And we denote it in symbols like this, F from X to Y, right? Now, here, the small y is called the image of X and small x is called the pre-image of Y. So these are some basic terminologies. Now, if for any two different elements, small x and small x dash belonging to capital X, there always holds that f of x is never equal to f of x dash. So basically, what are we saying here? If there are two different elements in set X and the image of both of these elements then can never be equal to each other, that means that we have a one-to-one function. So images of different elements are always different. That is the type of function known as a one-one function. You could also define it in this way. If f of x equal to f of x dash implies that x equal to x dash. That is also an alternative way of defining a one-one function. One-one function is also sometimes referred to as an injective function. So that is a class of functions that you should be aware about. We are going to define 2-3 different types of functions so that we can establish a correspondence between set x and set y. So this is the first class of function, which is an injective function. The second type of function we talk about is this surjective function, which is also referred to as onto. So here we say that if there is at least one small x belonging to the set capital X for each element y, belonging to capital Y, such that f of x equal to y. So basically every element in y, every element of y has a pre-image in set X, has a pre-image in set X. So that type of function is known as a surjective function or an onto function. And if a function is both injective and surjective, that is known as a bijective function. From f from x to y. So bijective function is a one-one onto function. So the basic idea of correspondence is if you have let x be a finite set, let x is a finite set, and if we can establish a bijection a 1 1 onto function from x to y, then we can say definitively that the number of elements in set X will be equal to the number of elements in set Y. So it might be true that in a problem, the number of elements of set X cannot be directly counted so easily. However, there is a different set Y whose number of elements is easier to count. So the standard technique here is basically to establish a bijection from set X to set Y if possible. And then you can count set Y easily and basically your job is done. Because when you have a 1 1 onto function, the number of elements on both the sides must be the same, right? If, for example, you had an injective function or 1 1 function from x to y, you would have said mod x is less than equal to mod y. Okay. So basically, this is the idea of the correspondence principle. We'll see it in action in certain problems, and then we will understand how to apply it. Also, we'll also talk about the technique of recursion. So it is best explained through some examples. So let's start with some questions, and then we'll see how to apply the technique of recursion as well. So the question 1 is this: let a circle be separated into n sectors, and these sectors are labeled S1, S2, Sn. Now, k different colors are used to color these n sectors, and we can assume that n is greater than equal to 3 and k is also greater than equal to 3. Each sector is colored with a different color from its adjacent sector. Colored with a different color from its adjacent sectors. So two adjacent sectors basically cannot have the same color, right? So we have to find the total number of coloring methods. Find the total number of coloring methods. So this is a problem where we'll use the technique of recursion. So let's first draw a rough figure, and let's say we have these sectors. This is S1, S2, and so on, and this is your Sn, right? So we will assume let A of n be the total number of coloring methods for n sectors. Correct. So if you think about it, you can try and figure out what will be the value of A3. So if there were only 3 sectors, think about it. Let's say these are the 3 sectors, sector 1, sector 2, and sector 3. Then the first sector, we have k choices, right? We have k choices for the first sector of colors. And then once you have fixed a color for the first sector, the second sector, you only have k minus 1 choices. So k minus 1 choices for the second sector. And for the third sector, you cannot use the color of this and you cannot use the color of this. So technically 2 colors are gone because the third sector is adjacent to both S2 and S1. So you have k into k minus 1 into k minus 2 basic choices. So for A3, the value is k into k minus 1 into k minus 2, right? Now what we will do is we'll generalize this. So let n be greater than equal to 4, right? So what we will say here is there are k different colors for S1, there are k different colors for S1 here, and there are k minus 1 colors for S2, k minus 1 colors for S2. So here S2 and S1 have different colors, right? Correct. So how many choices does S3 have? For S3, you will realize that there are k minus 1 choices. Why k minus 1 choices? Because S3 is in the middle. This was S1, S2, S3. Since n is greater than equal to 4, there is at least S4 here. It could be S4 and S5 and so on. So think about it. So far you have colored this with k choices, this with k minus 1 choices. But for S3, it is adjacent only to S2 that is colored right now. So only one color we can exclude. We cannot exclude the S1's color right now, right? So this also has k minus 1 choices, right? So basically, you can keep doing that, and then you will realize that even when you reach here, Sn, right? When you reach Sn, what happens? You have colored something here. So if, for example, we say that we take k minus 1 choices for Sn in order to be different from Sn minus 1, in order to be different from Sn minus 1, right? So if you keep counting like this, right now remember that for the last sector, we have a complication that the first sector is already colored, right? So for now, I'm ignoring the complication and I'm saying that total number of coloring methods are k into k minus 1 power n minus 1. Why is this there? This is basically k into k minus 1 into k minus 2, k minus 1 again, and k minus 1 again, so on. This is for S2, S3 till Sn, right? And I'm ignoring the complication that Sn is linked to S1 also. So actually the number of choices for Sn should be different from this, right? So basically what we have said here is this number ignores that complication, that Sn, you have to take into account S1 also. If we didn't have to worry about S1, this is the correct answer for the coloring method, right? So basically, this includes the case of S1 and Sn being in the same color, being in the same color, and the number of such coloring methods and the number of such cases. How many cases are there where S1 and Sn will have the same color? Think about it. By the principle of recursion, it should be an minus 1. Why am I saying that? So suppose you have to color it in such a way that S1 and Sn have the same color. What you can do is you can join them together and consider it as one big sector, right? This is one big sector, and totally now you have only n minus 1 sectors available. Not the n sectors, but since Sn and S1 have same color, they are one sector. So total sectors is n minus 1. And we said earlier that an was the number of ways to color n sectors. So an minus 1 should be the number of ways to color n minus 1 sectors, right? So basically what we have is we have to subtract this number from this calculation, right? To get the correct answer for an. Here we calculated an assuming we can do k into k minus 1 into k minus 1 forever, right? It included some bad cases. Those bad cases we have counted and we have said it is equal to an minus 1, right? So hopefully you have understood the point. So from here we get the equation an should be equal to k into k minus 1 power n minus 1 minus an minus 1, right? This is true for n greater than equal to 4. Now there is a simple way to solve this recursion. What we will do is we'll subtract. This is a recursive formula, by the way. An is being given in terms of an minus 1, right? But the problem is that this is a non-homogeneous recursion because this stuff is dependent on powers of n, right? It's a f of n, which is a power of n here. So the standard methods that we learned in a previous class, the characteristic equation method, that won't work. So we have to think of something else. So what I will do is an minus k minus 1 power n. So that will become k into k minus 1 power n minus 1 minus an minus 1 minus k minus 1 power n. So if you take a negative sign common here, you will get an minus 1 plus k minus 1 power n minus k into k minus 1 power n minus 1. And this part, let's simplify a little bit. You take k minus 1 power n minus 1 common, you get k minus 1 minus k, right? So this becomes minus k minus 1 power n minus 1. So what we have finally is an minus k minus 1 power n is equal to negative of an minus 1 minus k minus 1 power n minus 1, right? This is the situation that we are having. So now this is a simple situation where n is greater than equal to 4. So this series starts with n is equal to 4. And this is a geometric sequence. If you think of this as your Tn, this is your Tn minus 1, right? And we have the simple sequence Tn is equal to minus 1 into Tn minus 1. This is the GP with common ratio is equal to minus 1. And the first term starts with T4. So you have T4 is equal to minus 1 into T3. And then T5 is equal to minus 1 into T4. And you can easily find Tn from here. For n greater than equal to 4, Tn can be solved very easily. It's a GP. You can do it. I will just tell you the answer here. The final answer here comes out to be an is equal to k minus 1 power n plus minus 1 power n k minus 1. This is true for n greater than equal to 3, right? So what we did here in this question was use the recursion method properly. And what we did was basically assumed that the number of ways of coloring were an, and then we did a naive counting. That naive counting has some over counting. We have to exclude some cases from there. And the way we excluded the cases was we subtracted an minus 1, right? And then we just have to solve the recursion formula, right? Okay, let's look at another example. Question number 2. How many n-digit numbers can be constructed using 1, 2, 3, 1, 2, 3, so that there are no adjacent ones. There are no adjacent ones. Okay, so let's use the recursion method again. Let an be the number of n-digit numbers that meet the condition. Okay, so we have to make n-digit numbers using the three numbers 1, 2, 3. So there are no two adjacent ones, right? Now, if an is the number of n-digit numbers that meet the condition, you can check that a1 would be simply 3 because the numbers are 1, 2, and 3. And a2 would be 8. A2 would be 8. Technically, A2 should be 9, but you have to remove the number. There are total possible 9 numbers you can fit here, because 3 options for each digit, but you have to remove the case 11, right? So A2 is clearly 8, right? So when n is greater than equal to 3, we have already established some base values like A1 and A2, right? When n is greater than equal to 3, we can divide the n digit numbers that meet the requirement into two cases. That meet the requirement into two cases. The first case is if the rightmost digit is either 2 or 3. So if the rightmost digit is either 2 or 3, let's say these are the n spots, right? Let's say these are n places, and the rightmost digit is 2 or 3. Then what happens? The digit next to that, the second rightmost digit could be 1, right? Then could be 1, 2, or 3 actually, right? And after that, this could be anything as long as you satisfy the condition that if this was 1, it cannot be 1, right? You cannot have two adjacent ones. So if the rightmost digit is 2 or 3, we have full freedom to put 1 or 2 or 3 in this rightmost digit here, the second rightmost digit, right? So therefore, what we can say is there are n minus 1 ways to construct the number. Why n minus 1 ways? I will just explain with a more concrete example. So suppose n was equal to 4, right? We have 4 spots. Let's say there are total n ways to make the 4-digit numbers using 1, 2, and 3 such that there are no two adjacent ones. That is the condition of the problem, and that is what we have assumed. That an is the number of ways to make 4-digit numbers using 1, 2, 3 such that there are no two adjacent ones. So this is basically A4, right? We want to calculate A4. Now what I will say is case 1. If the rightmost digit here, the units place basically, is either 2 or 3, then this digit you have complete freedom. You can make it using 1 or 2 or 3, right? And after that, you have to satisfy the same sort of restrictions. So if you think about it, isn't it like filling 3 spots using 1, 2, or 3 without having two adjacent ones, right? So in case 1, when we fix the rightmost digit to be 2 or 3, we have the number of such numbers would be just how many ways can you fill the remaining 3 digits using 1, 2, and 3 without having two adjacent ones. But that is the definition of A3, right? So if you have an n-digit number, you have, if you fix the rightmost digit to be 2 or 3, then you have, in each case, you will have an minus 1 ways to fill the remaining digits, right? So that is case 1. And in case 2, if you fill the rightmost digit with 1, case 2 is if the rightmost digit is 1, then obviously this digit cannot be 1. It has to be 2 or 3, right? And after that, remaining n minus 2 spots, you can fill in an minus 2 ways, right? So again, there is a choice for the second rightmost digit. There are two choices. You have to put it as a 2 or 3. And therefore, again, there are 2 times an minus 2 ways here, total. This is for case 1, case 2, where the rightmost digit was 1, and for case 1, there was 2 an minus 1 ways, right? Because here the rightmost digit was 2 or 3, and remaining an minus 1 ways were there, right? So finally, using this logic, we are getting the simple recursion. An should be equal to 2an minus 1 plus 2an minus 2, right? This is a recursion of second order. You can put n is n plus 2 here. An plus 2 becomes 2an plus 1 plus 2an. And this second order recursion has the characteristic equation x square is equal to 2x plus 2. So x square minus 2x minus 2 is equal to 0 is my characteristic equation. The roots of the characteristic equation are 1 plus root 3 and 1 minus root 3. So the solution of the recursion should be capital A1 1 plus root 3 power n plus capital A2 1 minus root 3 power n. And finally, if you put in the data for A3 and A4, A3 and A4 are 22 and 60. Why? Because you already know A1 and A2. A1 was 3 and A2 was 8. So using A1, A2, you can find A3, A4. You can put in that data here and figure out the final formula by finding out the constants A1 and A2, capital A1 and A2. So I will leave that work to you, how to find the final constants A1 and A2. And basically, you should get this answer now. An is equal to 2 plus root 3 by 2 minus root 3. Not 2 minus root 3, it is 2 root 3. And here you have 1 plus root 3 power n plus minus 2 plus root 3 by 2 root 3, 1 minus root 3 power n. Basically, the values of capital A1 and capital A2 come out to be these. But the idea of the problem is done when you get this recursion. The solution of this recursion, we have learned how to solve recursions like this in the previous videos. So you just have to apply that method, and I have outlined almost how to do it. So just do that. Now, the next question that we look at is a very classic question. This is known as find the number of monotonic non-decreasing mappings from the set non-decreasing mappings from the set 1, 2, 3 n to 1, 2, 3 m. So first of all, monotonic means what? Monotonic is either an increasing function or a decreasing function. And non-decreasing, they have said it is non-decreasing. So what we have here is that if x1 is greater than equal to x2, then f of x1 should be greater than equal to f of x2. That is the meaning of non-decreasing, right? Okay. We have to find the total number of functions from this set to this set, as long as they are non-decreasing, right? Okay. So let's think about it in general. So suppose you had a function from this set to this set, f from here to here, and basically this function would be determined by how we assign the values of f1, f2, and fn, right? The values of f1, f2, fn determine what kind of function it is. So if it is a strictly increasing function, then what has to happen is f1 should be less than f2, should be less than, so on till ffn, right? So since here there are n elements in the domain and m elements in codomain, the number of ways we can select the elements for this range. For the range here, we have to select n elements out of the m possible elements in the codomain. So there is mcn ways to select the range, right? mcn ways to select the range. Once we have selected the range, once we have selected the range, there is only one way to assign them. There is only one way to arrange them so that it becomes a strictly increasing function. So in order to make it strictly increasing function, we have to arrange them in ascending order, right? So once you have selected the range elements, you just have to arrange them in ascending order, but the number of ways to arrange them in ascending order is strictly one. So if you were asked how many strictly increasing functions are there, you would have said it is MCN, right? Because the number of ways to do it is MCN times 1, right? But the question is asking us about basically non-decreasing functions. It is not a strict inequality, it is a less than or equal to type of inequality, right? So let's look at a concrete problem here. So since f is non-decreasing, the function is completely determined by how many values of j, by how many values of j belonging to 1 to n are assigned to equal k belonging to 1 to m. What do I mean by this? Let's say we have to find a function from 1 2 3 4 5 1 2 3 4 5 to 1 2 3 4 5 6 7 1 2 3 4 5 6 7, right? Now we have to say if two values are assigned to equal 3, one value is assigned to equal 4 and two values are assigned to equal 7. Two values are assigned to equal 7. Then since the function is non-decreasing, so first what are we saying? We are saying out of these 5 inputs, 2 of these inputs are going to be equal to 3, 2 of them. One input is equal to 4 and 2 inputs are equal to 7. So that will fix our function, right? All the elements of the domain will have different outputs, right? But we know that the function is non-decreasing. So what the non-decreasing part means that f of 1 and f of 2 must be 3 and f of 3 must be 4 and f of 4 and f of 5 must be 7, right? This is guaranteed if the function is non-decreasing. Like you cannot pick a different ordering of the inputs and outputs. You cannot say f of 1 can be 7. Why? If f of 1 is 7, then f of 2 has to be 7 or less than 7. So clearly the function will become a decreasing function, right? So once you are specifying how many of these are linked to which one of these, how many of the pre-images are linked to which images from the set of codomain, then automatically, because the function is non-decreasing, we can establish which ones are which, right? We can establish the exact function. So basically, what we are saying is, if I want to find out how many such non-decreasing functions are there, I just have to say how many different ways can we assign these 7 inputs amongst these 5, 7 outputs amongst these 5 inputs, right? So what do I mean by that? Basically, if you have f from 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5, 6, 7, right? Let's think of a problem where we solve the number of, we find the number of solutions of x1 plus x2 plus x3 plus x4 plus x5 . One second. Correct. X5 plus x6 plus x7 equal to 5. So there are 5 input elements which have to be assigned to any of these. What we are saying is how many will go to each of them, right? So you could be 0, 0, 1, 1, 2, 1, 0. This is a possible solution, right? X3 could be 1. So that is 3 has 1 input, 4 has 1 input, 5 has 2 of them, and then 6 has 1 input, right? This is a possible solution. So basically, what are we doing here? We are saying the 5 inputs are being given to the different outputs, right? So the number of solutions of this equation would be how much? There are 5 stars, and you need 6 bars here, right? So you will do 5 plus 6 C6 or 11 C6 in this case, right? 11 C6 ways to solve this equation. What we are doing here is every solution automatically gives us a non-decreasing function. So suppose I choose this solution 1, 1, 2, 1, 0, right? So one input goes to 3, one input goes to 4, 2 goes to 5, and 1 goes to 6, right? So that automatically means for non-decreasing function, we have to say f of 1 is 3, f of 2 is 4, f of 3 equal to f of 4 equal to 5, and f of 5 equal to 6. There is no other way to get a different non-decreasing function for this particular solution of the equation, right? Think about it. Are you able to find a new non-decreasing function that is not exactly this? You will be unable to do that. So what I'm saying here is, if you want to find the number of non-decreasing functions from one set to the other set, what you have to think is, think of the outputs as variables and the number of inputs here as the RHS of this equation, and think of how many ways you can distribute the inputs to the outputs, how many solutions are there for this equation. For each solution of this equation, you can construct one and only one non-decreasing function, right? So in the general case that we had earlier, so we have f from 1 to n to 1 to m, right? In this general case, we have x1 plus x2 plus we have xm. All the outputs are thought of as the variables, and the number of inputs here is n, right? The number of solutions to this by the stars and bars method, it is n plus m minus 1 c m minus 1, right? Okay. So this is the number of solutions for this equation, and for each solution you can make one non-decreasing function. So this is also equal to the number of non-decreasing functions from this set to this set, right? We have also seen that the number of strictly increasing functions would be MCN. That is the number of strictly increasing functions. You can apply it for small cases and check the validity of my statement. So take some small sets and try to actually list out the functions. You will realize that this logic works. Okay, let's go on to the next one. So this actually was an example of creating a function and counting the number of such functions possible. Let's move on to the next question. This one is the positive integer n is written as the sum of positive integers called, and that is called a partition of n, Now, if the order of the addends is different, if the order of the addends means the things that are being added are different, it is regarded as a different partition. It is regarded as a different partition. So for example, you have 3 can be partitioned just like 3, or 2 plus 1, or 1 plus 2, or 1 plus 1 plus 1. So this is one partition, this is one partition, this is one partition, this is another partition. There are 4 different ordered partitions for 3, right? We have to find the number of ordered partitions of n. Okay. So how do we do this one? Let's think about it. Right. So every integer, every number n can be thought of as a sequence of n ones, right? So right now you can think that there are n ones here. These ones basically make up the number n, right? So think about it. If there are n ones, then how many gaps are there between them? How many gaps are here inside, right? The number of such gaps is basically n minus 1, right? N minus 1 gaps, right? So my choice is basically, if I put a partition here, for example, think about it. If I put a bar here like this, I get one partition, right? I get 1 plus 4. In this case, I had 6. The number was n was 6. So I get a partition 1 plus 5, right? If I had put a bar here, then I get another partition 1 plus 2 plus 3. Think about it. 1 here, 2 here, 3 here, right? So basically what I'm trying to say is you can put bars or partitions in all the gaps here between the ones, and every different arrangement of the bars and the ones basically counts as a partition, right? So think about it. Each gap you get how many options? You have 2 options for each gap. What are the options? You either put a partition, put a bar, or don't put a bar, right? Don't put a bar, right? So how many total choices do you have to put partitions here? So for each gap, there are 2 choices and there are n minus 1 gaps. So the total number of partitions should be 2 power n minus 1, right? You have 2 into 2 into 2 till n minus 1 gaps. So the total number of partitions is simply 2 power n minus 1. This is one way to do the question. I will show you a different way also. The second way to do the question is to think of it like this. How do I split apart a number? I can say I can take only one variable and that is equal to n. This is one partition, one way, right? N itself was a partition, right? Now, suppose I have two variables, x1 and x2 equal to n, right? Now, how many solutions are there for this? All the different ways in which you can split it like this counts as different partitions, right? Because order matters in these partitions. So 1 plus 3 and 3 plus 1 are two different partitions. So how many solutions are there for this? This is by stars and bars method. You can say that there is one bar that is required and it will be n plus. Actually, each of the partitions has to be greater than equal to 1, right? Because 0 plus n is not a partition. 0 is not part of it. So we have to solve this equation, but each variable should be greater than equal to 1. So you will have to do a change of variable. x1 dash plus x2 dash will be equal to n minus 2. And now solve it by stars and bars method. And that will be n minus 2 plus 1 c1, which will be n minus 1 c1, right? Similarly, if you want three variables, again, you will have to do a change of variable first. x1 dash plus x2 dash plus x3 dash should be n minus 3 because each has to be greater than equal to 1, right? And now solve this equation. That will be n minus 3 plus 2 c2, right? That will be n minus 1 c2. So can you see a pattern? The first way was 1, which can be written as n minus 1 c0. The second way was n minus 1 c1. The third way was n minus 1 c2. And similarly, finally, you get a partition where you have n minus 1, you have n variables, right? x1 plus xn is equal to n. There is only one way to do it. This is n minus 1 c n minus 1. And that also adds up to 2 power n minus 1. This series also adds up to 2 power n minus 1. So you have one direct way to partition and the other way is a smarter way, which is the gap method that I showed, right? That is also another way to figure out the partitions here. Right. Let's look at the next problem. This is a very simple and standard problem. So I think it is question 5. There are n, and n is greater than 3 points on a circle. Every 2 points are connected by a chord. If no 3 chords are concurrent, no 3 chords are concurrent, find the number of intersection points. Find the number of intersection points of these chords inside the circle. So basically there are n points on a circle. Any 2 points are connected. Okay, so you will have a lot of lines here. Any 2 of them are connected, right? Now we are given that no 3 chords are concurrent at any point. So there is no third intersection here, right? So no 3 chords are concurrent at a point. You have to find the number of intersection points. So for example, this intersection point is inside the circle. This intersection point is also inside the circle. You have to count such intersection points. Okay. So that is the question ultimately. Count all the possible intersection points. This is also an intersection point that is inside the circle and so on. So if you think closely, draw a few figures, you will realize that whenever you take any 4 points on the circle, you can join them by chords and sides. But there will also be one alternative chord like this, right? When you take any 4 points on a circle, they make a convex quadrilateral. convex quadrilateral. And if you have a convex quadrilateral, the two diagonals will intersect inside the circle. And for each quadrilateral, there is only one intersection point. One intersection point inside the circle. Inside the circle. So if you want to count all the intersection points inside the circle, you don't need to directly count it. What you can count instead is count the number of convex quadrilaterals you can form using these endpoints, right? Because for each convex quadrilateral, you will get exactly one intersection, right? So this number is very easy to count. You will just say NC4. Any 4 points you have to select at a time, and NC4 will give you a convex quadrilateral, and all of those quadrilaterals have one intersection point inside the circle. So that's a pretty simple one, but you should know how to do it. The next problem is this one. Determine how many parts is a plane separated into by n lines in general, where no two lines are parallel and no three lines are concurrent. So we know that if there are two lines in the plane, you get 4 regions, right? 4 regions of the plane. Now there are n lines in the plane such that no two lines are parallel and no three lines are concurrent, right? So introduce an extra line here. Let's introduce another line like this, right? This is line 3. Think about it. Now the number of regions in general will become 1, 2, 3, 4, 5, 6, 7. So the number of regions is becoming 7. So R3, number of regions for 3 lines is 7 when R2 was 4, right? So introducing an extra line has increased the number of regions by 3, right? So what you will realize that this pattern holds. If you introduce an extra line now, the number of regions will become, this will be the 4th line. The number of regions now will become 11. You can count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we are missing one more region, this region, 11. Right? So what you will end up getting is, if n lines divide a region into an parts, then a1 is 2. You will get a3 is, a1 is 2, a2 is 4, a3 is 7, and the pattern is kind of obvious after that. The pattern is an plus 1 is equal to an plus n plus 1. The number of the line, suppose to make, if you introduced a third line, you are increasing the number of regions by 3. If you introduce the second line, you are increasing the number of regions by 2. If you introduce the n plus 1th line here, the number of regions increases by n plus 1, right? So this is a simple recursion that we get. We are getting an plus 1 minus an is equal to n plus 1. We need to solve this recursion. The solution of this recursion is pretty simple. You just keep writing all the terms like this. An plus 1 minus an is n plus 1. An minus an minus 1 is n minus 1 plus 1, and so on till A2 minus A1 is basically A2 was 4 and A1 was A1 was 2. So this is actually 2, which can be written as 1 plus 1, right? So if you add it all, you will notice that many of the terms get cancelled and you will end up with an plus 1 is minus a1 is equal to the addition from 1 to n here and plus n, right? Correct. So you will get n into n plus 1 by 2 plus n. You can simplify this and find an. An comes out to be n into n plus 1 by 2 plus 1. You should check these calculations yourself. You will be able to solve this recursion pretty simply. Just write the terms in 2 columns and find the sum. You should get the answer. Basically, write an plus 1 is equal to an plus n plus 1 and list down n starting from 1 onwards. Add the columns, add the LHS, add the RHS. You should be able to cancel many terms and prove that an is equal to this. Right? So that is the solution for this problem. But the main idea is to see the small cases and figure out the pattern, right? Okay. Now, the final question for this class will be this one. Find the number of subsets. Find the number of subsets of 1 to n that do not contain consecutive integers. Consecutive integers. Okay. You have to find the number of subsets of 1 to n that do not contain consecutive integers. So let's say let an be the desired number of subsets. Desired number of subsets. So I feel like I have misstated the problem here. Okay. Desired number of subsets of the set 1 to n, right? So if I wanted to do A1, then the set itself was 1 only, right? So the number of subsets of 1 that do not contain consecutive integers are 2. One of them is the set itself, 1, and the other one is the null set, right? And if you have the set A2, which is basically 1 to 2 set, how many subsets of this do not contain consecutive integers? 3 subsets. One is null set, one is 1, and one is 2, right? So basically what we are getting is A1 is equal to 2, A2 is equal to 3, right? These are the base cases of this question. You have to take the set 1 to n, create the number of subsets here that do not contain two consecutive integers, any two consecutive integers, right? Okay. So let's divide the problem into two categories. One is subsets do not contain n. Do not contain n. If the subsets do not contain n, then the remaining, they can contain n minus 1, right? They can contain anything from 1 to till n minus 1. Because we know that they don't contain n, so it is possible to include n minus 1. And they can contain anything from here, but again subject to the restriction that they can't have two consecutive integers, right? So basically, this boils down to solving the problem for an minus 1, right? So this is like solving a problem with n minus 1 elements instead of the starting point, which was n elements. Okay, that is case 1. And the case 2 is when they contain n. If they contain n, then they can't contain n minus 1. And now you can use only 1, 2 till n minus 2, right? So basically, we already know that the subsets have a n, but n is not consecutive with n minus 2 or any of these. So n you can sort of not think about. You have to think about how many ways to say non-consecutive integers subsets using just these numbers, right? So that will be an minus 2, because that is the problem for solving. That is the same problem as the original problem, but with n minus 2 integers rather than n minus n integers, right? We know that n minus 1 is not allowed in this case, and n is already there, but it is boiling down to a lower order problem with n minus 2 elements. So finally, using both the cases, you can come up with this recursion. An is equal to an minus 1 plus an minus 2. This is the recursion that we get. This is the same as the Fibonacci recursion. Fibonacci series also has the same recursion. So an is an minus 1 plus an minus 2. You can convert it like this. An plus 2 is an plus 1 plus an. And the characteristic equation becomes x square is equal to x plus 1. So x square minus x minus 1 is equal to 0. You will get two roots here. X is equal to 1 plus minus root 5 by 2. So your general solution of this recurrence would be an should be equal to a1 1 plus root 5 by 2 power n plus a2 1 minus root 5 by 2 power n. Now using some initial data, for example, we already know the value of a1 is 2, a2 is 3, and so on. Using some of this data, you can actually find out a1 and a2, right? So I will leave the solution of the recurrence to you, but the main idea of the problem was to establish the recurrence. So hopefully you'll learn something from this video. We have looked at several problems where we have solved combinatorial questions using the techniques of recursion. We have also seen how to count the number of functions from two sets. Remember that idea, that is very useful. We saw how many non-increasing functions we can make, how many strictly increasing functions we can make from two sets. So that concludes the lesson, and in the next video, we'll look at the principle of inclusion and exclusion. So that is a very important topic in combinatorics, and we'll look at that in a little more detail in the next one. See you next time.